Okay, it's 12:16, and I mean, people will still join us, but we can start the seminar. Hello, everyone. Welcome back to our Vanderbilt Machine Learning seminars for the fall semester. We are very, very excited to host Dr. Leon Bottou. Dr. Bottou is a prominent computer scientist and researcher. He has made significant contributions to the development of deep learning. And he was one of the inventors of LeNet and many other interesting work from generative modeling, the Wasserstein GAN, to large system of large machine learning systems. So Dr. Bottou has worked at prominent prestigious institutions in the past, including the AT&T Bell Labs, AT&T Research, NEC Research Institute, Microsoft Research, and more recently, Facebook AI Research, or Meta AI. His research interests span across machine learning theory, optimization, large-scale machine learning systems, and the practical applications of AI in many interesting domains. So it's really a pleasure to have him here. And Leon, with that, the stage is yours.
Okay, thank you very much for this nice introduction. So I'm going to present a talk called Memory Mosaics, which is, its purpose is to try to understand things. Can I go to the next slide? Is it going to work? Yes. It's a joint work with Jiang Zhang, who is a PhD student in NYU. Niklas is an ex-physicist who is working in Meta AI. Beidi is a professor in CMU, and Rana Joy is Beidi's student. And I'm going to start to explain what we're after. So you've seen many of the things, conversation with a machine. You can do that if you want. And what you see in this little text is that it's pretty easy to take a sentence and modify little parts, change things in a relatively detached way. And what this illustrates is that these machines have learned something interesting, which is the compositionality of language. That when you have a sentence, you can modify it, make changes, and manipulate it essentially to do plenty of things. You can change the things in a quasi-disentangled way. Sometimes you have to change other things, like if you change Jack into Mary, he's become her. You have some changes that are, but it's still complicated. And one important part of this is that we try to achieve something like this for years, and now we have it, and we don't understand it. So before starting by wondering whether LLMs can reason or do complicated things that are useful for business and that people want to see, I want to understand the basic phenomenon, which is that little thing that it does all the time. This is not something it does once in a while. It's something it does all the time. It's 100% of the case you're going to see that. So I want to know why transformers do these kind of things. Another thing is that compositionality can go too far. Like, how many codes should one eat each day? It is recommended to eat at least 2-3 codes each day, depending on your age, sex, weight, age, and it's typical hallucination, right? What's happening is that the compositional model mixes pieces of information that seem relevant, but in that case, there was not a sensible answer. So there is clearly a pattern of an answer that it applied to the wrong thing. And if you put the right information in context after that, are codes edible? Blah, blah, blah. So how many codes should one eat per day? And correct. So what you see here is that compositionality and reasoning, they're close cousins. Reasoning and hallucination, they're close cousins as well. So to some extent, when you're asking that the machine doesn't hallucinate, you're asking that it doesn't reason either. It's very easy not to reason at all. So I want to understand why and how. And I thought we have a little insight. We gain a little insight. But we'll make a detour because transformers are too inscrutable. There is a conspiracy theory, which is that the recipe of transformers have been given to Google by a robot coming from the future. One thing there are is that they're a bit, that's not true. No, no. I'm not advocating this. But you can repeat it, you go, it's funny. You can get people to react. They're also very complicated in the sense that they do some things, but like every machine learning system, they might do interesting things in ways that are not obvious by using internal mechanisms and everything. So we define what we call memory mosaic, which is a transformer-like architecture that's based on something we understand well, associative memories, and only that. And then we look what are the consequences, and there is one phenomenon that we can see. And there are some examples where we can show that it's actually working that way. And the third part is to show that this architecture is actually transformer-like because when you try it on the kind of tasks on which transformers work well, it works about the same. But at this point, it's already too complicated to understand. So an associative memory is an old concept in machine learning. And in that case, I'm looking at memories that can store key value pairs. You give a key, it returns an approximate value. Just a supervised system. There is a retrieval function that we're going to assume is invariant to permutation of the stored pairs. So you have this function where you give it a key, and there is a data set of key value pairs. And it's going to give you a value which you can interpret as expectational value given the key for a certain distribution. And one of the simplest way to implement is a Gaussian kernel regression. You say f of key and data set is 1 over normalization, sum of all the values weighted by some distance between the keys. It's just a smooth kernel. There are other ways to do it, of course. And if you decide to normalize the keys, you get the distance becomes a dot product and the sign goes away. So the interest of doing this with Gaussian kernel regressions is that they're easily differentiable and they're going to resemble transformers in very interesting ways. And here is what I call an associative memory unit. It operates on time series. Do not think of single examples, think about time series. There's an input time series xt, from which you're going to extract two other time series. One is keys, the other one is values. And then there is associative memory that stores them and gives an output. But there is a little trick. Here we're going to say that the key time series is looking just at the past. K capital T depends on the x's before and xt, while the value can look one step ahead. So basically what I'm storing in my memory units are little predictions. I'm just trying to predict one step ahead, something simple. So the feature extractor is trend. So let's see what's happening. At time t, I can compute the key from the feature extractor because I know x up to t. Then I can go in my memory, I can use the retrieval function of memory, compute my output. And at time t plus 1, I'll be able to compute the value because now I know xt plus 1 and store a new pair in my associative memory. So if you make a network of these things, you have to see that each memory unit is a little prediction machine. But what it predicts and how it does it is trainable. The value function, so I'm going back, the function that allows you to compute VT tells what they predict, and the key function tells how they predict it. And this is going to be trained. And the whole network is also a prediction machine, but its job is accomplished by distributing work to the little memory units. So it's interesting to look at it this way. So now the next question is, what do I say? It's very much like a transformer. So if I unroll this in time, I can see that yt here at a time capital T is a sum over all the past values stored in the memory of the weighting coefficients times vi. And what you see is that it looks like mask self-attention with a couple of differences. But there is slightly more aggressive mask because I can only go to t minus 1 because the value Vt is not known at this given moment. This slight shift is actually very important. There is no distinction between keys and queries. So it's a true kernel, it's symmetrical. Oh, wait, no. I'm working. No, leave me alone. Sorry, I have an intrusion. She's 5 years old. And there is no position encoding. So somehow what you see here is a kind of a bet about what's the first order effect of having different queries and keys. The transformer is famous for having computing queries and keys in a different way. And if you look in many simple systems using transformer, you realize that the only thing that's happening is that, for instance, if you have one of these raw positional encoding where the variable is rotated, the query is rotated from the key so that it can look in the past. So here we made it explicit. We made keys and values operate at different times. And as a result, we say, well, we know other higher order effects that we discovered later, but that's another story. And as a result, no position encoding and no distinction between keys and queries, because we claim that by shifting keys and values in time, deciding that values look in the future, keys in the past, we absorb the first order operation of having all this complicated system. So now, suppose you train such a system in time on sequences. So you have a bunch of sequences, and you're going to unroll your network in time and measure the prediction error at each time index. So what you see in this plot here is a bit an intuition. On the x-axis, you have the time index in the training sequence. On the y-axis, the cost at a given time step. So the curve tells you what the cost is, the prediction cost, the log likelihood, for instance, or the negative log likelihood, is at each time in the training sequence, average over plenty of training sequences. So you have a curve like this. And the thing you optimize is the area under the curve, because it's the sum over all the duration. And what you can see here is that on the right, you have a rich context. The memories have learned something. They can make reasonable predictions. What the memory is doing, again, is using the store data, which is the context, try to make a prediction about a prediction YT about what VT will be when I will know it at the next step. So if you have a big context, maybe it works. But when the context is small, there is no data and it cannot work. So you have a curve that's sort of like this. And by minimizing the area under the curve, the effect you have is that you're doing like this steamroller. You're pushing towards the left the space in which the memories don't do anything useful. So what you want to do is make the memories return useful results as quickly as possible after the smallest possible context. Does it make sense? So I repeat, you want to make the memories give useful prediction after seeing the smallest possible context. So what you have is a bit like a meta-learning. The thing that you want to optimize, the learning you want to optimize happens at inference time, is the storing data into the memories and using that data to make predictions. And the actual training of the network is a meta-training because it's trying to make the memories work more efficiently, give useful results as quickly as possible on each sequence. So how do you do this? How do you make memories quick like this? So let's look again at the Gaussian regression, the Gaussian smoothing equation. And there are things that are well known, like you need to learn the bandwidth. If you have a Gaussian smoothing regression, you need to have the right beta, the right smoothness of the kernel to predict. You can learn the kernel, which is mean learning the key, because the key is a trainable function. By learning the key, you can learn the kernel. But there is something else you can do, because you have many of those. you can learn the VI, you can learn what to predict, which means that you learn how to split the overall prediction task into subtasks that are best modeled independently. And when I say best, it means in the sense of making the memories as quick as possible. If there are questions, maybe too many people online is difficult, but if there are questions, please ask.
Yeah, I have a quick question, right? So the reason we don't need positional encoding here is because we are using the mask attention, and that mask attention is essentially avoiding the network to be permutation equivariant.
Not exactly. It's a bet. The bet is that the main use of having different keys and queries and queries and keys is to match previous positions. So basically, yes, the system is permutation invariant in a transformer, and you rely only on the position encoding to do something like bigrams.
Right.
If you take something like what's called an induction head in the work of the entropic guys, you see you have two layers of transformer, and the only thing the first layer does is use the position encoding to put together the bigrams or the n-grams. And the way you do it is by encoding in the query a version of the key that's been transformed to what it would have been one step before.
I see.
So if you say this is the only thing you're using this for, you can just get rid of them by explicitly making them look at different things. So if you get the keys in the past and the value in the future, then you get the induction head in one layer for free.
Got it. Thank you.
You're going to do bigrams and n-grams pretty well, easily. Now, if all these systems, position encoding and query key, also have other purposes, and if these purposes are comparable in importance, then this wouldn't work at all. We would be in trouble. So that's why we have to make further experiments to show that this is the case. But now I'm asking you to consider the system we're using, where we simplify all that stuff by basically making this time shift and removing key query distinction and position encoding, and look at its consequences. And the consequence that we see is because now we can interpret each memory unit as a little prediction machine, we can start discussing how the big prediction problem decomposes in smaller prediction problem, which is a bit what we're looking at the beginning. At the beginning, I told you I want to understand composition. And for this, it's interesting to understand how the big problem decomposes in small problem. So having the big machine being a prediction machine, because it's going to predict the next word, for instance, or predict something about the future, and having it made of machines that do predictions as well, allows me to see why I have this decomposition. Does this answer the question?
Yes, that makes sense. Yes, so there is also a question in the Q&A. Do memory mosaics synergize with vector embeddings for performant inferencing? I'm not sure if I understand the question. Maybe you understand.
No.
Yeah, so we need more.
There's probably something meant to be there, but it's difficult to express in a little text.
Correct.
The memory mosaics, for me, they're more a system to understand what's going on. They might give interesting engineering opportunities, but that's a secondary interest for me. And it's about removing the things that are complicated and trying to see something. So this is why I found attractive to express the big prediction machine as a composition of small ones.
Right.
So these two, the two on left, learning the bandwidth and learning the kernel, they're known ways to make Gaussian smoothing faster, more statistically effective. The right one, learning what to predict, exists only in a system where you have plenty that you can, it's about the composition part, right? And basically, the claim is that such a system is going to split, it's going to decide what each memory is doing by disentangling the global task into subtasks that are easily model independently. Now, look that this is different from what we used to do before transformers. Like before transformer, there was plenty of hopes to discover the structure, interesting structure in plenty of things, plenty of learning systems. And the recipe was to use a cost that was goodness of fit, like the likelihood, and maybe some sparsity regularization in the hope that in the sparse pattern, you would see something interesting. And it always failed. When you do something like this, it's a bit different because now the cost is rigged in such a way that what you want to do is make sure that you adapt quickly to a slightly different sequence or slightly different distribution. So it's not a single distribution business. It has to do with how sequences are different and how you can adapt quickly to each sequence. So I'll go to the next step. So I call this predictive disentanglement. I said that already. And here's an example. Suppose you live on a planet somewhere, and there are 3 moons around your planet. And you're an astronomer. You, before the Greeks, you don't know anything about celestial mechanics, but you still would like to predict the position of the moons. And all our astronomers, they decide, okay, let's make tables. So the first astronomer says, I'm going to make a table. I'm going to log the joint position of all 3 moons. And if one day I see a position that I've seen already, I can just read in the table what's going to happen the next days. And in order to do this, you need to log all possible positions of the 3 moons. So if the periods are compatible, you need a number of entries, which is the least common multiple of all the periods. Quite a long table. Now, astronomer B is a bit lazier, and he says, no, I'm going to log the position of each moon independently. Then I'm going to look at each of them independently. And if one is at the position I know, I'm going to predict the next position of that moon independently from the others. I'm going to put everything together. For the moons, as long as the moons don't collide, it's probably right. But the table it needs now is the max period. Sorry, my slide is wrong. The maximum period of the periods of all the moons. Now, what you see between the maximum period and the least common multiple, you have an effect that's exponential in the number of moons, right? It's a huge effect in terms of the length of the tables you want to have. And the question is, can you actually learn this with the kind of mechanism that I described? So, okay, let's do this. So that's my network, a single layer of either 1 or 3 memory units. The feature extractor, it's here, is just a linear function. The value extractor is a linear function, but of xt plus 1. And then I have a combining layer that's going to mix the various predictions when I have several, and that's going to give me the output. So my parameterization is just 3 matrices, they complex 3 by 3. Complex because moon position are well expressed by a complex number. So that's that. And if they happen to be all identity, it's a good solution. So this network has 54 weights, which is 9 times 3 times 2, because they're 27 complex or 54 reals. And it's going to work, which tells you that compositionality is not something that comes from scale. This is awfully small scale compared to normal transformers. Okay, so when we learn with just one memory head, so this is a graph where essentially I plot the periods of the moons for one of the sequence, because each sequence has different periods, right? The black vertical lines are the period of the 3 moons, and the red one is the least common multiple. And we have to choose one where the least common multiple is not too large, otherwise we cannot show anything. So what you see is that when you run this with one head, essentially you need to see a number of examples that's the total period of the system or the least common multiple of the periods, and after you can predict, like astronomer A. Now, if you have 3 heads and you train, training is a bit difficult. It looks like an XOR, you know, it just, sometimes it gets a bit strange, but most of the time it works. you'd see something like this. After the first period, the error improves because you can predict one of the moons. After the second, it improves. After the third one, it improves to the total result. And in between the maximum period and the least common multiple, you have plenty of situations here where you have moon configurations you've never seen before. But you're still able to make a prediction because you've seen each individual moon in that position before. So I say it's a very simple form of composition where you're able to predict something you haven't seen before, that's quite far from what you've seen before. But that if you model it as disentanglement, as disentangled moons, it makes perfect sense. And essentially, this system learns this. So what you get here is a very simple disentanglement, but with only 54 weights. So it's not a question of scale. It's really something that has to do with the architecture. So now you ask me questions about whether what I'm doing in this system is justified. Basically, does it work like a transformer? And to know that, you have to go to language, right? Now, language is big as inconvenient. I didn't want to do big and inconvenient. So first of all, we decide to stay as close as possible to a GPT model. So on the left, you see a classical GPT-2 transformer as attention heads and as a feed-forward net. On the right, we see what we're doing, where you have these memories here. And here, the FFN is replaced by what we call the persistent memories. It's not something that makes a big difference, but it's conceptually interesting. So basically, it's exactly the same thing as the CMEM, except that this time, you don't have values. All the stored values are learned by gradient. And the idea is to model two kinds of information that's specific to a particular sequence, information that's persistent across all sequences. So the contextual memory in it is this business here. So this is what I've shown before. And it's a bit more complicated than the version that we had for the planets, because we want to know a little bit more of the past. So we use the leaky average of past keys instead of just the pass key. Helps a little bit. If you were just using a convolution would work too, but okay, we use the leaky average and a convolution for V, go figure. It doesn't make a huge difference at this level. And we use normalization so that the dot product of the keys is the same as a distance. All things that, a normal transformer can do plenty of flexibility there. We didn't allow any flexibility because we want to see exactly what's happening. The persistent memory units, the one at the top, are exactly the same, except that the KV pairs that are stored are trained by gradient. So the idea is that we want to use exactly the same kind of memories, but with a different scale. Instead of being trained at the level of the sequence, they train across all sequences, with the idea that you could invent memories with intermediate scales if you wanted to. And they're exactly the same, it's the same code. To test this, we train on, maybe there is the Microsoft paper on tiny stories that I found very nice, where they basically say, we're going to use a large language model and make it generate little stories that are suitable for a child 3 to 4 years old. And we're going to learn that. And the idea is that we learn something that's a language very simple, but it's also a very small world. There is daddy, mommy, the ball, the toys, the pet, and that's about it. It doesn't have to know much about the world. The interesting thing is because the language is very simple, there is room to learn some of interesting things. Even though it's a simple word with daddy, mommy, the pet, the toys, there are things you need to do to make good sentence. You need to have a consistent stories. Characters shouldn't appear and disappear. Names should be consistent. And if you train a GPT model size on generic English, you don't see any of this. But if you train it on a small data like this, you see some interesting effects where you can assess some semantic abilities. So I like this thing. Alloyers liked it less. they asked us to create a new data set because they don't want us to use tiny stories because it's been generated from GPT and everything. So there's some legal complexities that were very frustrating. So eventually we generated another one with the mixed trial model, go figure. That was the recommendation. And but it's very similar. And what you can see is that the continuation of various prompts. So the tiny story guys give a bunch of prompts where they test plenty of properties, and they're perfectly reasonable. If you look at the training for various depth, so the transformer and the memory mosaic, the architecture, so they're designed to have the same number of parameters for every depth in terms of blocks. So they're extremely comparable. At depth 1, the mosaic is a bit better. It's because one layer of mosaic is able to do the induction head. The transformer needs to. And beyond that, they test really the same. One aspect of this is because we did something that you should never do if you want the best performance. We trained the mosaic with the hyperparameters that are optimized for the transformer. So we didn't try to optimize the parameters for the mosaic because that's another story. So we want to compare precisely. And when we look at this, we were satisfied that our bet, which is that distinction key queries and position encoding is all a system that mostly serves to do n-grams. Our bet on the first order seems to be validated. That's a small model. Yes?
Certainly, on one quick question, at the same depth, memory mosaic has fewer number of parameters, correct?
No, they're the same.
Oh, the number of parameters.
We made sure they're the same.
Okay, got it.
Right. So that's just if you look at the architectures, they're already very comparable. You know, they have the same number of heads here, and this has heads of the same size as below and adjusted for the same number of parameters.
Right, but transformer has queries, but
yeah, you get a little bit less parameter in the queries. We put them here instead.
I see.
And then also, yes, you can play a little bit, but it's not a huge difference anyway. So we just adjusted for the same number of parameters. You could also replace the PMEM by FFN. It would work the same, really. But the CMEM and attention head, there are some difference that we can see. So now we're going to do something which is to start to take our system out of distribution. So there is a variant of Wikipedia that's called the Simple English Wikipedia, which is a relatively small subset of the Wikipedia pages that have been rewritten in simple English, closer to what's in the tiny stories. But what you have to see as well, that simple Wikipedia is a lot more complex than the tiny stories. It's not about daddy, mommy, pets and toys anymore. It's about plenty of things. And the articles are much longer. The tiny stories, they're 100, 200 tokens long. And the simple Wikipedia is typically 1,000 tokens long, at least. So when you take the system trend on the tiny stories, on the baby stories, our version, whether a transformer, a Mamba, or memory mosaic, and you run it on simple Wikipedia, we have to be clear, all these systems suck. None of them is really good. But you see an interesting difference that's very stable. And the difference is that when you start to go beyond the length of a typical story, the mosaic wins there by a substantial margin, meaning that out of distribution performance seems to be to show a delta. That's clear. So we wanted to look at this more closely, and there is a test called RegBench, an in-context learning benchmark. So RegBench is entirely artificial. What they do is that they create a lot of artificial languages. Each of them is a little probabilistic finite automaton, like a hidden Markov model, essentially. So they draw 100,000 of those. They kept some for testing. And the question is, you train on a certain number of those, which is the horizontal axis, from 100 to 100,000. And you're going to test on the unseen ones. So that means that when you test from the test is sorry. The sequences that we're using, they're made of about 20 words generated by these stories with a separator. And the task is to predict the last character of the last word, the last one in the context. And so basically you have the beginning of the sequence, and they're not very long, 20, the words, a couple hundred tokens. You have a couple hundred tokens to learn what this particular probabilistic finite automaton is about, so that you can predict the next word. And the Rackbench guys, Urek and co, did plenty of experiments and plenty of models. So all these curves are their curves below, except that we replicated the transformer to be sure. And what you see is that transformer is not bad. It's here. It's, actually, the left curve is accuracy. The right one is more interesting. It's total variation distance, meaning that when you predict the last word, you actually predict the distribution of the last word that you can compare with the theoretical distribution that comes from the PFA. It's more than comparing with one word. And so basically after 1,000, after seeing 1,000 languages, the transformer is pretty much able to predict what's happening. But the Mosaic is way better at this game. We were very surprised to see such a difference. And we have to see how it scales. That's another story. And that's due to the context mem. If you change the persistent memory by FFN, you still have the same thing. It's just the way the prediction is set up. One possible reason is that the memory mosaic can do induction head in just one layer with less parameters. So all this benchmark has a well-defined protocol for optimizing the hyperparameters and everything. We just use their code, essentially. So I go to the conclusions. How am I in time? Oh, not too bad. But I lost my... I'm still sharing?
No, you're not.
Okay, I messed it up. That's bad. Share again. Okay. So the conclusion about the why and how. So we have shown, actually, we got a glimpse, it's not perfect yet, of why and how memory mosaics split the prediction problems into disentangled components and recompose them when provided with unseen context. This was already visible on the moons. You provide a system with a configuration of moons that is never seen before, is able to disentangle the various moons, predict each of them separately, recompose. Second, the memory mosaic, the way we defined it, is epsilon away from a transformer. So chances are that transformers do more or less the same things. I wouldn't say that the memory mosaic does something that transformer doesn't do. And the little thing about the in-context learning might just be of less inefficiency, something small. The caveat is that we still have lots of things to understand in how multiple layers of memory units cooperate. In one layer, it's easy. When you have multiple layers, well, it's more difficult to understand. But we can start using this framework to try to understand a bit more. Less important conclusions. There are interesting engineering opportunities. If we're speaking of associative memories, there are plenty of ways to implement associative memories like hashing, locally hashing, hash sensitive, and so on. And the better in-context learning abilities are interesting, but that might also mean that they hallucinate more. I don't care. I like hallucination because it's closer to reasoning. But I know that some people who want to use large language model don't want hallucination at all. I think it's bad taste. Hallucinations are cool. This is what's interesting. And there is some ongoing work, like a scaling work in progress. And what I can tell you is that so far, no blocking factor. We went to 1.5 billion, no problem. But what we found is opportunities to observe and understand interesting effect. I told you that on the first order, the difference between key and query are doing things that are due to exploiting position encoding to do n-grams. But we can starting to see second orders, things that were not visible at the scale of the paper, but are starting to be visible that we can understand. So it's sort of interesting. We'll write it a little bit later. And I work about alternative implementation, like locality sensitive hashing schemes, but it's always complicated engineering. When your premise is that you're going to use the CPU to go faster than the GPU, you have a big barrier to overcome. It's actually doable, but it's hard. And changing the memory implementation. Associative memories can be implemented in lots of ways, like I say, locally sensitive hashing, but also outer product associative memories. And that's related to the ZEP operators XLSTM, in fact. And so these are opportunities to see interesting things and to understand a little bit more. And that's the talk. So I can take more questions as necessary.
Fantastic. Yes, let's thank our speaker, at least the panelists. Please unmute.
Yeah, thank you for the great talk.
Thank you.
I have a question. I start the questions. So the persistent memory, like you mentioned that it is learned over like the entire input tokens. It's not just for a specific. So like that's very much similar to the idea of prototypical neural networks. Essentially, it includes some prototypes, correct? Like, is that understanding true?
Yeah, it's actually okay. So we wanted to stay close to GPT. GPT has this big FFN, lots of parameters there.
Right.
Also, it's obvious that you need to learn things that remain across sentences. So we were wondering how we can do the FFN in a way that's informative. And we came up with that very simple idea. That is the persistent memory comes from a work by Saina Subbata a while ago. And we just say, well, we're just going to use memories, but instead of storing things inside the memories at every step, everything will be pre-stored, and we're going to learn it by gradient.
Right.
So this is what we did. Now, if you look at the FFN, what's happening? The first layer, let's take a simple network with one hidden layer, not a complicated swigglue or something like this, right? And suppose you have a pretty much strong activation, like let's say sigmoids, right? You can see the first layer as selecting a few hidden units, typically quite sparse. And then the weights of the second layer are averaged according to what the hidden units give. The thing is that the number of points that are activated in the hidden unit is variable. When we do it that way, essentially there is each head is doing these things independently. So basically, in each head, the thing you sum are weighted by something that has a softmax. So instead of being, let's say, a sigmoid nonlinearity, it's like a softmax, and it's applied by groups. So you can see, you could implement it like a FFN. The first layer of the FFN is essentially the same, but then you do group softmax, and then you have a layer above, and that would give the same thing. So you can make it just as fast as the FFN if you want to. But in that case, we thought it was conceptually interesting to have the same thing. So we took exactly the same code and the same process, even though it was a bit cumbersome. Turns out it doesn't make a difference. It's interesting to understand what's going on. Like, for instance, if you have multiple prediction problems on several layers, you decompose the prediction in multiple sub-prediction sub-problems, but they're on several layers. And in between, you have something that routes the information from one little predictor to another one, and so on. And these PMEMs, they do all of the routing, essentially. They tell you how you're going to route stuff between layers, between the contextual memory. The little predictors are here. And this is what routes the information between the predictors. But you can also say that if you take CMEMs in distant blocks, the CMEMs of the intermediate blocks are also part of the routing network. So the route is adaptive. So this is why understanding the multiple layers is more complicated. But what you see essentially that you develop a kind of modularized prediction function. And some parts of this modularized prediction functions can be adapted quickly on the sequences you see.
Right. So the CMEMs there, if I think about, I tend to think about the transformers in the form of like system of interacting particles, right? Like so that CMEMs allows for interaction between tokens or interaction between particles, but the PMEMs, very much similar to the FFN, doesn't allow for communication or interaction between particles. It's applied individually to the tokens.
Yes, except that if you look at the CMEM, is very constrained because the CMEM is storing all the key values without order. It's permutation invariant. The CMEM can be viewed as something that models the distribution of y given x, that permutation invariant. The only thing that gives a time direction here is the shift between the value and the key.
Yeah, and that's why it's important, right? Because if it is not there, then we have a permutation equivariant system.
If it's not there, you do nothing, right?
Yeah, right.
Now, in a normal transformer, it would be permutation equivariant if it were for the position encoding.
Right.
So here we remove the position encoding, we remove key value distinction, which is necessary when you have position encoding. But we added this this permutation breaker in the simplest possible way, which is just the value can look one step ahead from the keys.
Brilliant. Yep. There's a question in the Q&A. How does the architecture scale to long contexts?
So that's the beginning of an information here. The articles on which this model was trained are the baby story article there. They're 100 to 200 tokens. The simple Wikipedia things is much longer. So it's working quite well. I don't know if there is a graph. Let me see if I have the graph somewhere in the hidden somewhere in the menu. Oh, no, I don't want to do that. I might have a plot somewhere. I just don't know if it's in that talk. There's a plot in the paper. Okay, let's get the paper. I'm going to show that plot. No, it's not here. It's in downloads. Okay, the kind of plot you want to see for that question. So let me change the sharing now. I have to go back to the Zoom. No, that's not the right Zoom window. Ah, yes, it's here. So I have to share something else. It's here. Maybe I should zoom a little bit more. No? Can I? So if you want to look at long memories, you would like to see how on various layers the weighting factor in the Gaussian process or the weighting factor in the attention in the network depends on the token position, right? So what you see on the left is the GPT-2 on the baby story stuff. And it's a big zigzaggy because of the position encoding that's trained. On the right is on the memory mosaic. And what you see is that, sorry, this is when you are the last token. You're on the last token of a 500 window, and you look how it attends to the previous positions. Does it make sense? On the GPT-2, you see a lot of zigzagging because the position encoding is trained that creates a lot of variety. On the mosaic, you see that it's a bit strong at the beginning, and that's because of the leaky average. Then it's entirely flat to the end. So if you do the same thing, but extend it on a longer memory block, you get the same property. It's completely flat. Here is that if you use the rope. So in that one, the rope was trained on something like, I think the windows were 600, something like this. So here the rope works, and when you beyond the training window, it becomes crazy. And this is the alibi, which is basically it's weighted down with the distance. So that seems to be interesting for long context. One of the things we're trying to do with the bigger models is to see how they expand to longer context and trend without any fine-tuning. So with the ROP, there is no hope that it's going to work. With alibi, it barely works. And with the mosaic, we have to be a bit careful. We have to do things about the bandwidth, because when you're starting to have a longer and longer context, the bandwidth should be adjusted. See, we didn't have a bandwidth adjustment in the existing system. So this is the kind of little phenomena that we're learning when we're scaling up. So of course, it requires not just scaling up, but paying attention. So testing the system out of its normal range. You know, if you do MMLU, you don't see anything interesting. If you try to look how my trend network is working when I extend the memory, when I get out of distribution, when I change things, you started to see interesting effects.
And there is a follow-up question from Jesse. Does that suggest that at some very long context length, you saturate and functionally attend to nothing?
Well, this is an average attention weight on different sentences. When you look at a particular sentence, it peaks somewhere, right? This is average on many sentences. This is attention pattern average on many sentences.
Mm-hmm.
So when you have a particular one, it peaks where you have a match, right? But this is why when it's very long, you need to change the bandwidth, because you want a kernel bandwidth that's much narrower to pick on the right information, because now you have a choice. So you somehow have to think how you're going to evolve the kernel bandwidth depending on how much is stored in your memory, which is the kind of thing we had to work on essentially.
And like going to the kernel bandwidth, right? Like, so you have this parameter beta, I think you use beta for, right? Like, so
let's go back to the slides. Yes, I have to find the zoom. Where's the zoom? No, I done it. If I click this, no. I want to go back to zoom. No, it's not the right one. There's a zoom window somewhere.
Yeah.
Not that one. I cannot find it, so I cannot change. I'm going to do that. I'm going to say stop share, and I'm back to the zoom. Yes, and
yes.
I can go back to the slides. The slides, yes. Okay, so the beta business.
Yeah. So that first, like, is it different for different layers of the network? So, or like it's constant throughout, and how sensitive is the approach?
So looking at the keys, this is how we compute the keys. We multiply xt by a matrix given a k tilde. We do a leaky average. We normalize, and you multiply by bandwidth. Now, all these things, the matrix, the leaky average coefficient, and the alpha, they're specific to each head. But the scaling factor here doesn't depend on the position in the context in this current version. What I'm telling you is that if you want to have very long context, you need to make it dependent on the position. So the more you store in the memory, the more narrow the bandwidth you want.
Got it. And there is a question from a practical perspective. Is there going to be a Hugging Face repository for the mosaic nets
or
memory mosaics?
Well, right now, the thing that we describe is something you can train in a couple hours, you know? Like the GitHub we have, you get your machine with just one GPU and you train it in a couple hours. So we kept it small on purpose because I think that, I told you that we can see compositional effect with 54 weights.
Right.
It means that I don't buy that it's all scaling. There is something else going on. And so I wanted to do it small. Now we have to grow a little bit in size because, first of all, when we want to reviewers ask for it, they lack imagination. They want to see how it scales. Well, in fact, I thought that the insight is more interesting, but okay, they want to see how it scales. And also because there are a bunch of little tests that you can only compare when you have at least, let's say, a 7B model and you compare with other 7B models. But this is not really the important thing. The important thing, I think, is the insight that we get, which is very partially just the beginning of something, but we're starting to understand how it works and why it's doing what it's doing. And the fact that we can, if we pay attention, you can see how various elements of the transformer of the mosaics are actually doing things. But in order to do that, you have to constrain it like we normalize here. This normalization is an annoyance. It's a constraint on the network, right? Because it makes the alpha fixed. If you don't normalize, the network has sort of find its way and having a kind of adjustable bandwidth, more or less trend. And basically, if you go to long context, you have to fine-tune because it's the only thing you're going to fine-tune. But you don't know because you haven't seen. At least when we do it that way, where we try to keep the system to be as close as possible to a plain vanilla associative memory we understand, and epsilon away from a transformer as well. When something is too strict, we see that it doesn't work and we have to think about it. So you see, it's not a game to try to get the best performance. It's a game to try to get the best insight.
And I can't emphasize how refreshing it is to hear that from you, that sometimes reviewers lack imagination, right? Like it's the competition of like who is the state of the art all the time is not the most important thing. Sometimes insight, I think most of the times insights should matter more. So I completely agree with that. It's very refreshing to hear it from you. Yeah.
But just actually, we are a huge part because there was something strange in the narrative reviews that we found, and we were a bit surprised. And eventually, Jianyu found a website somewhere in ChatGPT doing automated paper reviews. So we sent our paper, of course, to see what the review is. And we got a review that was not very imaginative and making sense, better than you would expect in terms of logical, with a very nice summary. And heads that were very close to those of the reviewers. And some sentences, not all of them, of course, some sentences were a perfect match. And so what you see is that if you listen to TV with the New York Times and everything, they tell you, if you don't do AI, you're going to be obsolete. So what do you do if a young reviewer? You use AI, right? You put your paper in the system first, then you get a review, with the review, then you read the paper and you copy paste, right? The same way you do for homework.
Right.
The problem with that, so first of all, it's not that catastrophic because the reviews are not that bad. The problem with that is that you get n times the same review pretty much, right? The interest of having multiple reviews is that you get a diversity of reviews with diversity of opinion. People read different things, they see different things. But here, now everything they see is essentially a variant of the first read. And the first reader was the transformer, was not the person.
Right.
So the kind of lack of imagination is something that we're going to have to live with, right? It's a bit annoying. So you see when they say, AI is going to dominate, and with the progress of science that's so fast, we're going to lose control and everything. No, we're not going to lose control. The progress of science is going to stop because the system is going to kill it.
Yeah.
So, okay, fine. You can look at it that way too, just.
Right. Yeah, that's certainly a problem. Yeah. Okay. Any other question? Last question. We are at the end of the hour. Oh, there is one more question from Jesse. Do you think that the layers will tend to learn hierarchical representations that will be more interpretable than that was found in BERT? As in, will mid layers learn parts of speech and the top layers learn discourse structures?
I've been doing neural nets for a long time. My permanent experience is that looking in what the neurons are doing is just like reading tea leaves. No. Take a ConvNet. People say, oh, this is a cat detector. This is a dog detector. Nonsense. It's none of that. It makes nice pictures. It looks good in the paper. But in practice, what each unit is doing is way more complicated. Maybe it's a cat in a particular context or something you don't see, something you cannot summarize with a single word. So basically, my experience tells me that there is no way we can understand precisely what everything is doing in a larger language model. What you can understand is what are the pressures that are going to give you representation of a particular kind. Look at biology, for instance. In biology, you can do butterfly collecting, like Chomsky said, or you can look at the tree of all animals and classify everything. But that's useful. These are facts, right? But it doesn't you don't understand anything. The only way to understand biology is to understand things like the evolution or the natural selection principle, and then they start to tell you why the biology you see is that way. Now, it's not perfect, but they tell you why. And it's even something you can use. Like if you want to, let's say, breed bacteria that are going to eat petrol that you're going to be able to use to clean petrol problems somewhere, you can just breed them and it's going to work in a few generations. You're going to get bacteria that thrive on petrol. It works. So I really believe that the only way to understand something like this is not to understand the details, but understand the pressures and understand what they imply. To give you another example, suppose you want to do AI, human level AI. We're not there. You cannot explain everything because you cannot explain everything within the context of our intelligence. You cannot explain human intelligence, every detail of it, within the confines of our own intelligence. You have to use abstraction. So even though I'm not going to say bad things about people who are doing good work, trying to see what the units are doing and they do honest work, they're trying to look seriously. I'm thinking that it's more interesting to look at the principles. But to look at the principles, you need to make small things, small experiments. The stupid 3 moons problem with 54 weights, I think is more enlightening in that respect. Because in that case, I know what every weight does. That's easy to see. Now, if you have 54 million or 54 billion, I'm not going to be able to say.
Right. Yes. That's, I mean, I tell my students that if it doesn't work on MNIST, it probably doesn't work on something more complicated, right? Like that's like, but do you think that's true? Like something that doesn't work on like smaller scale is not worth spending time on larger scale? Right?
It's not super clear. Like take XOR network with backprop. I don't know if you tried. It's difficult. Just do the XOR. You have two inputs,
Yeah.
1, 0. You want to do the XOR problem, one of the first backprop networks.
Right.
It's actually tricky.
If your network is large enough, optimization will work like almost 100% of the time. But if it is a small, like yes, like
if it's minimal, it's small. So one of the problem of our 3 moon problem is that it's minimal by design.
Yeah.
So it's a bit tricky. So sometimes you see this kind of a problem, but so you have to use a good judgment. You know, if I cannot solve my problem at all, probably if I can solve by over-parameterization, probably it's going to work. But then when you grow up, like for things that work for MNIST, don't work that well on natural images. You have to do some extra stuff in terms of normalization helps a lot, for instance.
Right.
And so when you increase, you discover new things. But you have to do it little piece by little piece and take your time, which is difficult these days because everybody is in a hurry. And try to understand what's going on. You know, our job is to understand, right? More than doing. You know, you have a big engineering committee of people who are doing things, our role as a scientist is to understand so that we have understanding they can use to do things.
Great. I really thoroughly enjoyed this talk, the conversation and the question and answers. We really appreciate your time, Leon. And yeah, we thank you again. I hope to hear more from your successful career and like many more years of you contributing to this field of AI.
Okay, thank you very much.
Yep.
I was glad to speak. Bye-bye.
Bye.
Thank you.
Thank you.
Bye-bye.